This video covers essential idea number 2 in our nuclear chemistry unit. Essential idea number unit is the following. Radioactive atoms, by definition, spontaneously decompose. But other non-radioactive atoms can be made to decompose if we bombard them with a particle. The most popular example of this is the bombardment of a uranium-235 with a neutron. Upon capturing the neutron, the uranium atom, now it's captured a neutron, so it's now technically uranium-236, that becomes unstable and splits into two smaller atoms and ejects some neutrons, and lots of energy comes with it. So the purpose of this essential idea is just to distinguish between those radioactive atoms that spontaneously decompose and those that can be made to decompose by bombardment. So what we see in the nuclear equation here is, this time we have two particles on the reactant side, so to speak. That's because we've got this uranium-235 atom. I think its half-life is billions of years if it's just left alone. But we can engineer it through bombardment, with bombarding it with a neutron, and then we can instigate the atom splitting. So when it accepts the neutron, it becomes unstable. It splits into two smaller nuclei and then ejects. This is saying 3 neutrons. So this part of it right here is the symbol for a neutron. And for neutron, neutrons, remember, atomic number comes from the number of protons. And so with no protons, we're going to put a 0 in the subscript portion. But it is a particle of relative mass, right? The protons and the neutrons we add up to get mass number, so that's why you're seeing the 1 here. We happen to eject 3 of them as a result of this process, so that's why there's the coefficient of 3 there. And the image below is of exactly this. So here's our uranium-235, here's the neutron that we're bombarding it with, and here you can start to see the fission of the uranium-235 into smaller atoms. We create a krypton, we create a barium, and then we've also got 3 neutrons that are ejected at high speed as well. So these two go, the equation and the first image here go hand in hand. This is just another example of bombardment. So this is bombarding a nitrogen atom. So if we bombard a nitrogen atom, we create an unstable atom. So once the 2 protons and 2 neutrons from the alpha particle, from this projectile here, as it's mentioned, become part of the nitrogen nucleus, it then becomes a fluorine because it's got 2 more protons. But that particular isotope has an unstable ratio of neutrons to protons, and so it undergoes decay. And it ejects what would be a single proton, creating an oxygen atom. Okay. Another important point on this is that in the case of uranium, you can create a chain reaction. And this is really fundamental to both uranium used for energy production and uranium used for weapons. So this first part here, and this is just showing 2 neutrons coming out, but the idea is fundamentally the same. So we start with our uranium-235, and we bombard with a neutron, and then that forms the krypton and the barium, and we'll say some number of neutrons. But we now have high-speed neutrons that can then bombard other uranium-235 atoms in your sample. So again, this concept will apply to both energy production and for nuclear weapons. So now that we've started a chain reaction, we have these 2 nitrogen that are going to bombard these 2 uranium-235 atoms. They then split. They then send 2 more neutrons off. So now in this third stage, we can now have 4 uranium atoms. And they're going to split, and so on, and so on, and so on, and so on. And so if each one of these is releasing some amount of energy, and you start this chain reaction, you have enormous quantities of energy being released. Okay, that looks like that's all I had for that one. So the idea here is we've covered essential idea number 2, and with that there are some fundamentals that you can talk about, and then you can say, gosh, maybe I'll research nuclear energy for a few minutes, or nuclear weapons for a few minutes, and or bombardment in general, and come up with some aspects of it that you've learned about that weren't necessarily presented here. Okay, thank you.